In this video today, we're going to look at what exactly happens in a redox reaction. And then we're going to see how to take a redox reaction, which is spontaneous, and use it to create an electrochemical or voltaic cell, basically a battery. So first of all, what's happening in redox reactions at the atomic or particulate level? Okay, feel free to pause the video, by the way, as you need in order to take down your notes. So let's consider a very common chemical reaction, one that most students have seen at some point. So we've got a test tube, if you look at the picture for a moment, a test tube with a blue solution of copper sulfate, copper 2 sulfate. So if you were to look at that solution, you would see lots of water molecules, but then once in a while you'd see a little copper 2 plus cation, and you'd see little sulfate anions. So, but mostly it's water with those ions floating around. Then into that blue solution, we put a piece of zinc metal. Now, zinc is a solid at room temperature, and as a metal, its atoms are in a very regular pattern. We call it a crystal lattice structure. So here in the picture, you can see these little gray circles. Those are the atoms of zinc as they're in the solid state. They're all stuck together, touching each other. So we've got this zinc strip dipped into the solution of copper 2 sulfate. Now, if you do that, you'll almost immediately notice that the surface of the zinc metal starts to blacken, starts to turn color. And then if you leave it for a few minutes, you'll notice that there's more and more precipitate forming on the surface of the zinc. And what appeared originally as a bit of a blackish precipitate, pretty soon you notice it's actually a reddish brown precipitate. And then in addition to the precipitate, the color of the solution starts to fade. So the blue color, which was caused by the copper 2 plus aqueous ions, that's what caused it to be blue, those copper ions floating around in the water, that blue color starts to fade. It gets a little bit lighter, and after a while, depends how concentrated the solution was, but maybe 30 minutes or 45 minutes later, the solution is no longer blue at all. There's no blue left, which of course means there's no copper 2 plus ions floating around in the water. And instead, we have a lot of precipitate all over the surface of the zinc metal. All right, so in this common reaction, the overall reaction can be written in a molecular format like this. Zinc reacts with copper 2 sulfate and forms zinc sulfate and copper metal. And a grade 11 student would look at that and say, that looks like a single replacement reaction. All right, so during the reaction, the zinc metal appears to dissolve. Where we had solid zinc originally, at the end we have zinc sulfate, which is really zinc 2 plus cations and sulfate anions floating around in the water. The blue copper solution turns colorless because essentially all of the copper 2 plus ions that were in the solution become copper metal precipitate on the surface of the zinc metal. So if you look closely, you can see that that's actually, we can reduce this to a net ionic equation. The sulfate ions would just cancel from both sides, and we have this bottom equation at the bottom of your slide. There's the net ionic equation for the reaction. Feel free to pause again if I'm going too fast for you to write stuff down. In this net ionic equation at the bottom of the page, notice that the zinc atom starts off with an oxidation state of 0. So on the left side, you should put a little 0 above the zinc. The copper 2 plus starts off with an oxidation state of +2. So put a little +2 above the copper 2 plus in this equation. After the reaction, the zinc is now zinc 2 plus, so put a little +2 above the zinc 2 plus. That's its oxidation state. And then copper at the end has an oxidation state of 0. It's just copper metal, the precipitate. So when you put those oxidation states in, it becomes evident that the zinc is being oxidized in this reaction. Zinc is losing 2 electrons for each atom, while the copper 2 plus ions are being reduced. Copper 2 plus is gaining 2 electrons to become copper metal, the precipitate. So this reaction is definitely spontaneous, meaning it goes to completion. It's got a very very large equilibrium constant. Okay, that's a better way to say what spontaneous means. The equilibrium constant is greater than 1, so it favors the products. Looking at the picture, we can see that the blue color essentially disappears. At the end, there's really no blue visible, which means this reaction is pretty much complete. The copper 2 plus concentration pretty much goes to 0. And in its place are zinc 2 plus ions, which must be colorless because the solution at the end is a colorless solution. So we have here a spontaneous redox reaction. Right? Copper 2 plus reacts with zinc metal spontaneously, and a redox reaction happens. Electrons are transferred from the zinc, which was losing electrons, to the copper 2 plus, which was gaining the electrons. And then the products are formed. So whenever we have a spontaneous redox reaction like this, we can take this reaction and use it to create basically a battery, to create a device which will produce electricity that we can use. Right, here's another image of what's happening. You decide if you need to add anything to your notes. There may not be much here to add, but looking at the picture, the blue solution of copper 2 plus and the silvery zinc metal strip. The zinc metal strip is darkened in the solution because precipitate is starting to form on it. Looking at the atomic level and thinking of like collision theory from our kinetics unit, the copper 2 plus ions are mobile. They're free to move around in the solution. The zinc atoms in the metal strip are not moving around. They're in the solid state. So once in a while, a copper 2 plus ion collides with the surface of the zinc metal. In that collision, electrons are transferred. Zinc atoms lose electrons, and the copper 2 plus ion gains the electrons. Then the copper 2 plus is now copper metal. It's just neutral copper after gaining electrons, and it sticks to the surface of the metal. The zinc, which lost electrons, is now zinc 2 plus, a cation, and it floats away into the water. So over time, you have less and less copper 2 plus in the water, and you have more and more zinc 2 plus. So you'll have less and less blue color to the solution, and the zinc ions in water are colorless. So eventually the solution turns colorless. So how do we actually get in there and use the spontaneous redox reaction to generate electricity? Keep in mind grade 9 science. What is electricity? It's the movement of charge. Usually we think of it as the movement of electrons through a wire, but more generally, it's the movement of charge. If you have charged particles moving in one direction, then there's an electric current flowing. So how do we make use of the electrons which are being transferred from zinc to copper and use that, say, to light a light bulb or to run a radio or something? How do we use it to generate electricity? So during this redox reaction, let's remind ourselves, zinc was losing electrons, being oxidized, while the copper 2 plus cations were gaining electrons. They were being reduced. Those are the two half reactions. When electrons are on the right-hand side of the equation, they're being lost. When electrons are on the left-hand side of the equation, they're being gained. So the zinc is being oxidized, copper 2 plus is being reduced. So electricity, again, is the flow of charge. So how do we get in there and use this reaction, which is clearly transferring electrons? Electrons are charged particles. How do we use that to create a battery? The key idea is we have to prevent the copper ions from colliding directly with the zinc metal. When they collide directly, the electrons are passed from zinc atoms to copper ions, and we cannot use those electrons. So we're trying to use the electrons to light a light bulb or to do some work for us to basically operate something. But if the copper ions collide directly with the zinc metal, we can't use the electrons that are transferred because they're transferred directly from a zinc atom to the copper ion in the collision. So what we need to do is separate the copper ions from the zinc atoms. In other words, don't put the zinc metal strip directly into the copper solution. But we have to provide a path. We have to provide some way for zinc, which wants to give its electrons to copper. We got to provide a way for zinc atoms to send their electrons to the copper ions. So the key is to separate them and provide a pathway for the electrons to go from zinc to the copper. What we're starting to describe right there is what's called a voltaic cell or a battery. So here is a picture of an electrochemical cell. Now, again, a better, perhaps a more accurate term would be a voltaic cell. You're going to see that coming up in just a moment, or even a galvanic cell. Electrochemical cell is a very broad term. So it's a device that uses the spontaneous redox reaction, like the one we've just been talking about between copper ions and zinc metal, to produce electricity. So take a moment and pause the video and sketch the picture that you see here. So you can see we've got two beakers, two containers. One of them contains a zinc 2+ solution, and one of them contains a copper 2+ solution. In your diagram, I hope you've sketched this, label those solutions as being 1 molar. So when they're 1 molarity concentration, and when the temperature is 25 degrees Celsius, then this voltaic cell is operating under standard conditions. So standard conditions, 1 molar concentrations, 25 degrees Celsius temperature. So we're going to describe here a standard voltaic cell. Now in the left-hand beaker, there's a strip of zinc metal. We put a piece of zinc metal into the zinc solution. In the right-hand beaker, there's a strip of copper metal. So we put a piece of copper metal into the copper solution. And we connected those two metal strips with wire. Now, each of the metal strips is referred to as an electrode. You can see that word there, an electrode. So there's a zinc electrode and there's a copper electrode, the two metal strips. We have more specific terms. If oxidation is occurring, then that electrode is called the anode. So the anode is the metal strip where oxidation occurs. If you recall, in this reaction with zinc and copper, zinc was getting oxidized. Zinc was losing electrons. So therefore, the zinc metal strip here is the anode. The cathode is the metal strip, the electrode, where reduction occurs. So remember that. Oxidation occurs at the anode and reduction occurs at the cathode. So in this reaction, copper 2+ ions get reduced at the copper metal strip. Zinc atoms in the zinc metal strip get oxidized. So zinc is our anode, copper is the cathode. To connect the two beakers, we've got a U-shaped glass tube. So it's a hollow glass tube, and it's full of salt water, a pretty concentrated solution, in this particular case, of potassium chloride. There are little K positive ions and there's little Cl minus ions. Potassium chloride is a type of salt. It's a soluble salt. And there's a solution of potassium chloride in that salt bridge. The purpose of the salt bridge is a couple of things. It's to complete the circuit. So if we don't connect the two beakers, we won't have a complete circuit for electricity to flow. Electricity is going to flow from the zinc strip where electrons were being lost. Those electrons will travel through that external wire, through our light bulb and light the light bulb, and then they're going to flow over to the copper strip, where the electrons will be gained and reduction occur. But that will only happen if the two beakers are also connected, because we need to have a complete circuit for electricity to flow. Another way to think of the salt bridge is that it prevents the buildup of electric charge. That's an important thing you'll want to make note of. The salt bridge prevents buildup of electric charge in the two beakers. Pause the video if you need to write that down. The salt bridge prevents the buildup of electric charge in the two beakers. How does it do that, and why would there be a buildup of charge? Well, consider the zinc beaker. Electrons are leaving the zinc beaker. Electrons are negatively charged. If something negative is leaving this beaker, then this left-hand beaker could acquire a positive charge. It's losing electrons. Those electrons are flowing into the copper beaker. Electrons are negatively charged, and as they flow into the copper beaker could acquire a negative charge. So we don't want that charge, positive in the zinc beaker, negative in the copper beaker, to build up. Why is that? Well, if the zinc beaker is allowed to get a positive charge, then that positive charge will prevent more electrons from leaving the zinc strip. The electrons which are negative will not want to leave from a positively charged beaker. They'll be attracted to it. Likewise, the negative charge that could build up in the copper beaker could prevent electrons from coming in there. Because electrons are negative, they don't want to flow into a negatively charged beaker. So we have to prevent the two beakers from becoming charged, and that's where the salt bridge comes in. The potassium ions of the salt bridge are positive. So every time a negative electron enters the copper beaker, a positive potassium ion flows in. A positive potassium will cancel the charge of the negative electron, and that prevents the copper beaker from becoming negatively charged. Likewise, every time an electron leaves the zinc beaker, a chloride ion, which is negative, will flow into the zinc beaker. So as the zinc strip becomes positive, as it's losing electrons, it attracts the chloride anions. As the copper strip becomes negative when electrons flow in, that will attract the potassium cations. So notice anions from the salt bridge, the chloride ions, are headed towards zinc, while the cations, the potassium ions in the salt bridge, are headed towards copper. Because anions are heading towards zinc, we call the zinc strip the anode. Because cations are heading towards the copper strip, we call that strip the cathode. So they get those names because of the ions that they attract. They attract ions with those charges because the zinc strip, after losing electrons, becomes positive, and that will attract the negative anions. The copper strip gaining electrons becomes negatively charged, and that will attract the positive cations from the salt bridge. So the salt bridge completes the circuit and prevents that buildup of charge. Now, I mentioned earlier that this device is more generally called an electrochemical cell, but more specifically, it's called a Voltaic cell, named after an Italian chemist named Volta, who was the first person to build one of these things. And it's sometimes also called a galvanic cell, named after another Italian named Galvani, who also was an early pioneer in electricity. So this is basically a battery. We're taking that reaction which spontaneously happened between zinc and copper and using it to send the electrons from zinc through a light bulb on their way to copper, where they'll be used in a reduction reaction. So there's oxidation happening in the zinc half cell, and there's reduction happening in the copper half cell. This redox reaction is being used to light a light bulb. It's being used as a battery. Now, when you have a battery, there's often on the side of the battery an indication of the voltage produced by that battery. Most little batteries that we use are 1.5 volt batteries. That voltage is actually the unit of what's called cell potential. The voltage is the unit for cell potential. So I'm going to use here an analogy to help understand what the cell potential of a battery actually is. Think of a waterfall. We know that water spontaneously moves from the top of the waterfall to the bottom because there's a difference in potential energy from the top to the bottom. There's a higher potential energy at the top of the waterfall and a lower potential energy at the bottom. So the water flows from the higher potential energy position to the lower potential energy position. It's the same reason a ball falls down a hill and doesn't go back up on its own. It'll go down the hill because it's going from a higher potential energy at the top of the hill to a lower potential energy at the bottom. So things tend to go from a higher energy state to a lower energy state. They don't on their own go the other way. So why is it that electrons are flowing from zinc towards copper? Why were the electrons headed from zinc to copper, but not the other way around? It's a similar argument. The electrons in the zinc metal must have a higher potential energy than the electrons in copper metal. So therefore, electrons from zinc will flow spontaneously towards copper in the same way that the water flows down the waterfall from a higher potential energy to a lower potential energy. So there's a difference in potential between those two metal electrodes, between zinc and copper. There's a higher potential in the zinc and a lower potential in the copper. We call the difference in potential between the two metal strips the cell potential, and we give it the symbol capital E subscript cell. And then we often put a little degree symbol beside that. So there could be a little degree symbol beside the E cell. The degree symbol would mean that this is being used at, or being measured at standard conditions, 25 degrees Celsius, 1 molar concentrations, 1 atmosphere pressure if gases are involved. So if you see a degree symbol beside the E cell, then it's called a standard cell potential. The units for cell potential are volts. Okay? So sometimes the cell potential is called the voltage or the cell voltage. So when you see the 1.5 volts on the side of your little battery that you're putting into your device, that's a 1.5 volt battery. That's the cell potential produced by that battery. Right? Now, in any redox reaction that is proceeding spontaneously, so if we're talking about the redox reaction from electrons going from zinc to copper, and the one we've been discussing, the voltage will be a positive number. But if you talk about the reverse redox reaction, so if we wanted to talk about electrons going from copper back towards zinc, then the cell potential would be negative. So when there's a positive cell potential, you're talking about a spontaneous redox reaction. A negative cell potential would be for the reverse reaction, which is non-spontaneous. So we're going to stop there in this little video. We'll talk more about cell potentials and how to measure them. We have a table of reduction potentials in our data booklet. We'll look at that in our next lesson.